Hello, everyone, and welcome to today's SANS webcast. Opening the Floodgates, how to analyze 30 plus terabytes of endpoint data without drowning your security team. Sponsored by Red Canary. My name is Carol Auth of the SANS Institute, and I will be moderating today's webcast. Today's featured speaker is Brian Beyer, CEO and co-founder of Red Canary.
Thank you, Carol. All right, welcome everyone. Today, as we look at how we are opening the floodgates and analyzing this data, we're going to start with a quick introduction of why we do this. We're going to move into a technical deep dive, look at some lessons we've learned of doing this over the last 4 years, end with a case study, and then answer any questions you have. So first, why do we do all of this? Why do we look at endpoint data? The first assertion I'll make is that most of your security investigations are going to lead you back to your endpoints. Whether it's an event or an alert that started from endpoint logs or other systems you have, or if it's a network-based alert from anything monitoring your perimeter, in many cases, all of that data leads you to one fundamental question, which is, then what happened on the endpoint? And so investigations lead back to those endpoints. The second assertion I'll make is that there's a lot happening on your endpoints. This is where your users are. This is where applications are running. This is where adversaries are attempting to get to. A lot is happening on those endpoints. To give you an idea of scale, we pulled some sample data from one of our customers, an organization with roughly 10,000 endpoints. And you can see roughly what's the scale of data that we're looking here. One thing we've learned is that every organization is very different. Some organizations have certain tools that produce 5 to 10 times the amount of activity as others, but this is a good sample. 120 gigabytes of data coming from endpoints every single day. Billions of file creates and modifications, billions of registry modifications, and all of this coming from roughly 70 plus million processes that are starting and stopping throughout every single day. If you look at that data, what you may think is, whoa, that's a lot of data. If I start looking at that data right now, I don't really even know where I'd start. And that's why we're here today. So one of our goals is that we want to move beyond alert-driven security. Right now, a lot of security programs operate off of alerts coming from different products, placing them in a SIEM or an MSSP, and then investigating the ones that we can get to. What we want to do is move beyond the alerts from those security tools and start looking at all of the data that's happening back on our systems. So with that, with those two assertions and this goal, what we want to do is start diving into the technical pieces of how we do this. So if we go back to all of that data, you might be sitting there with blurry Keanu Reeves face on saying, whoa. Nobody wants to be blurry Keanu Reeves. What we instead want to do is, after today's walkthrough, we want you to feel more like this Keanu. Yeah, you're going to be a little beat up. You're going to be a little bruised. You've been through a little bit of a battle here, but you're going to be ready to tackle all of that data from your endpoints, and you're going to be able to use it to build a better security program. So when we start doing that, let's talk about the requirements that we need to have for a system who can process this amount of data. The first requirement is we want it to scale massively. We want to be able to allow our business to grow without having to rebuild our security architecture or our data architecture as we grow. A lot of the organizations we work with, they grow in fits and starts. They may grow, at a good clip of 20, 30% year over year, and then acquire a new organization and double or triple in size overnight. You don't want to have to re-architect your security program every time that happens. You want to be able to scale with your business as it grows. Our second requirement is that we want this to be low maintenance. It's easy in a lot of cases, if you're a big tech company who has existing data pipelines, to be able to borrow some of the system administrators or the site reliability engineers from them to help you operate your security program. But to many businesses, We don't have the ability to do that. So we want a system that's very low maintenance so that we can keep our team focused on security things, not software and systems administration. And our third requirement is that we need a platform that allows us to very rapidly prototype and add new techniques and capabilities into our platform. When we're analyzing this data, we don't want it to be a small number of our team who can actually add new capabilities. We want everyone on our security program to be able to add and contribute new ways to detect threats. If you see a new technique on Twitter, if you go to a conference and learn about a new adversary tactic, we want it to be very simple for you to prototype that and plug that into the platform without requiring a big bang release. So given those requirements, here's the process we're going to talk about today about how do we process this data. So we start by collecting, we then standardize it, we're going to detect any interesting activity, we're going to suppress that which we've already investigated before, we're going to investigate what's new, and then we're going to remediate. One of the things that's always stuck with me is a quote that I heard on a presentation years ago talking about complex systems like this that process massive amounts of data. The quote goes something along the lines of this: a high-quality complex system is made up of many simple systems. You'll see this as a common theme throughout what we talk about here today and lessons we've learned in building this system. For a system that is going to be very complex like this, there are a lot of simple components who make it up. And so it's key for us to be able to keep those focused and simple because they make everything move faster when we're in production. So let's get started with the first step of this. When we look at how we're going to collect data, as we walk through this process here, we start with endpoint sensors. So these are sensors. In Red Canary's case, these are Carbon Black Response, they're CrowdStrike Falcon, they are Windows systems you may already have emitting sysmon data. Those endpoints are producing telemetry about either activity of processes and users on the system, or they're also feeding us information about the actual binaries and applications who are executing on those systems. That data comes from the endpoint and comes up to a collection platform. Think of these as your EDR products, again, like Carbon Black and CrowdStrike, who are collecting all that data in a central location. Now, when we start talking about building our pipeline of how we process this data, what we want to do is we want to get that data into our pipeline by putting it into an S3 bucket. And we call this the native bucket because data who comes into here is going to be in the native format of the endpoint sensor. One of the things we've learned at Red Canary is that the ideal format for this data coming in are gzipped files filled of new line separated JSON records. It's a very simple format. Every tool you use out there can decompress these files. They can process over hundreds of thousands of lines of JSON. It's all very simple and a fundamental data type. So now we'll introduce one of the first AWS components that we talk about of building a system like this, an SNS topic. So the way this works is that inside of AWS, we can set up a notification so that every single time we place a new file in our S3 bucket, we're going to get a message on an SNS topic that tells us, hey, we have a new file to process. This combination of an S3 bucket with an SNS topic is one of the fundamental data types of how we process this data. So one of the things we want to talk about is how are we actually going to make that bucket and that SNS topic a reality inside of AWS? For those of you who haven't used it before, Terraform from the HashiCorp team is a must-use, absolutely required open source tool in managing AWS resources. Before Terraform, you either had complicated API scripts that were set up to use the AWS APIs to create resources, or you had teams who had to go into the AWS web console and attempt to create resources there and tie them together. In this case, what Terraform lets us do is define this infrastructure as code. So in this case, if we go back to our picture, the first thing we want to do is we want to make an S3 bucket. This is what the Terraform definition of creating the bucket looks like. You can see we're creating a bucket called Floodgates native. We have lifecycle rules that are going to move this data to AWS Glacier after 30 days so that we save on costs. And then we're going to completely expire and delete that data after a year. Very simple, defined as code, can be templated, can be version controlled, peer reviewed by your team. Terraform is absolutely fundamental to this. The second resource we'll create in AWS is that SNS topic that tells us a file has been added to the Floodgates native bucket. And then finally, we link these two together. We create a bucket notification that every time an object is added to the bucket, then creates a message on the SNS topic that says, hey, everyone, I have a new file to process. So now that we've introduced that, let's talk about the first application we build into our pipeline. We have these files of native data being placed in an S3 bucket. We have messages notifying us about them in an SNS topic. And now we have what we call the standardizer application. So this is a key application for us and for your teams as well, because it's going to perform the translation of data from whatever format it comes in from your other tools into a common and standardized model that all of your downstream applications can depend on. What you don't want to do is build downstream applications that have a bunch of checks in them and a bunch of conditions to say, if I got this data from data source 1, treat it this way. If I got it from data source 2, treat it a different way. Instead, what we want to do is we want to abstract that all away and do this standardization at the very beginning of the pipeline so that adding new data sources only modifies this one component and doesn't have to affect everyone downstream. In order for this application to work, we need to introduce another AWS resource called an SQS queue. So what a queue lets us do is subscribe to this topic, and every time a message is added to the topic, it goes into our queue that the application can then process and work off. You'll see we also in the picture talk about a dead letter queue. So this is a concept that allows us to be a lot more resilient to failure. One of the unique things about how these queues work in AWS is you can say, hey, if you haven't responded back to the queue and said, yes, I have successfully processed this file in a certain amount of time, the queue is actually going to assume that you've either died or failed to process that message, and it's going to put it back on the queue. And you can say, hey, queue, if after 4 or 5 retries of processing this one file, go ahead, if it still fails, put it on this dead letter queue for QA. This is how we make the system resilient to any failures. If you're a standardizer who's running and processing a file and something happens in that AWS region and that component goes away, the SQSQ will see that and say, hey, I never heard back. I'm going to go ahead and reprocess that. It makes it very simple to be highly failure resilient. So now let's talk about, again, how do we use Terraform to make that a reality? In this case, what we're going to do is we're going to make our SQSQ. You can see we have that visibility timeout, which says after 90 seconds, go ahead and put it back on the queue if we haven't heard that we successfully processed it. We have a redrive policy who says you have 4 tries in order to process this message before we put it on the dead letter queue. And then in step 2 here, we subscribe that queue back to our SNS topic. So this is how we've now linked our S3 bucket to our SNS topic to the SQS queue that our standardizer application is going to use. Finally, in step 3, we create that dead letter queue that holds those failures for QA and for debugging purposes. So now let's talk about what does that standardizer component actually look like? Remember, we want all of our components to be as simple as possible because that makes them simple to build, simple to debug, and simple to deploy. And so the standard blueprint for any component of processing these data files here, is going to start with a trigger that tells us we have a new set of data to process. It's going to have a component that does the actual work, and then it's going to have an emitter, which takes the results of the component processing and puts it somewhere else. And you can see in this standardizer example, in the pseudocode, this is exactly how most of our components look. And if you follow this blueprint, you can keep simple components like this as well. We have a SQS trigger that says, hey, I have a new file to process. Our component goes and gets the file out of S3, referenced in the message. For every one of those lines in the file, we parse out the JSON, translate it from native format to standardized format, then format the record so we keep things all tidy. We want to downcase MD5s everywhere. We want to, ensure that process names are tidied up if they might have, bad characters in them. And then we take that JSON and we emit it back to a string and collect it all together back into the new line separated file. That then goes to our emitter, which goes out to our S3 bucket. This is the standard blueprint for a component that is very simple and your team can start using right away in order to process data files like this. So now we have standard data nicely formatted in a simple way that we can use throughout the rest of our system. And now we can look at how do we actually build detection applications on top of this data. So the first example application we use here, let's talk about threat intelligence. Generally, it's one of the simplest components to build because you maintain this map of intelligence. Maybe it's first party, to your team, that may be indicators that have been used against you in the past. For Red Canary, it's indicators we get from monitoring all of our customers' environments, from breach responses we're involved with, all that data even created by our internal R&D team. It may be open source indicators, it may be third party, it even may be binary reputation sources like VirusTotal or Reversing Labs. So that application gets its own SQS queue, and then every single piece of data who processes through the system runs through that application. And so that application may sit there and say, hey, if I see a bunch of cross-process events, maybe I'm not going to care about those. But if I see any network connections, I want to check the IP and domain of that network connection and determine, is this something that flags threat intelligence? If it does, the output of our threat intelligence application goes into a tip-off bucket that we call Intel tip-offs. Same process as before. One file comes into the application, one file goes out. Anything that looked potentially threatening goes into that tip-offs bucket. The second application, and this is really where we got our start at Red Canary, is with behavioral analysis. We're going to take every single bit of endpoint data happening on your systems. We're going to maintain this huge database and state mapping of every single process on every single one of those endpoints. And we're going to be looking through that and attempting to identify any behavior that looks like an adversary technique. If you're familiar with the great work that the MITRE team has done with the attack framework, they've mapped out hundreds of adversary techniques and tactics that can be used. This is where those come into play for us. We're looking for specific patterns of behavior that map those techniques. You'll see that R there, that's an RDS database for us. In fact, it's a fleet of RDS databases. Frankly, it's one of the harder systems for us to scale because it is a database and those tend to not scale very horizontally. In your organization, you're probably looking at a smaller scale than we are. A single, Postgres database there or something running in RDS should serve you very well. So now in this example, we've detected interesting activity in two different ways with two different applications here. Each of them had their results put in their own bucket. And so now we move on to, what we recommend as the suppression step. This is something we've learned from years of doing this, that a lot of security programs try and deal with the volume and noise of data by cutting back their detection coverage and trying to turn a blind eye to some of the more noisy techniques or indicators. What we actually want to do is we want to sit there and we want to figure out how can we look at all of this data, but not have to repeat the same investigations over and over. And so we do that with what we call suppression, which is really asking this question for every single potentially threatening event. We're asking, have I investigated this specific technique being used against this specific application on this endpoint, running by this user, maybe with a specific parent process? And if I've already investigated that set of conditions before and said it was okay, then I can suppress that event and I don't need to see it again. Think of this as highly, highly refined and targeted suppression of patterns of behavior you've already investigated. A lot of security tools give you the ability to turn off certain detection techniques and maybe say, hey, don't show me that if you see PowerShell exhibit that behavior again. What we want to do is we want to target that down and refine it even further so that we don't possibly miss anything, but we don't have to repeat the same investigations over and over. What you'll see from an architecture perspective is now we've actually done this combining back together of two different parts of our pipeline. We have two different buckets, one for tip-offs based on threat intelligence, another bucket based on tip-offs from behavioral analysis, and they each have their own SNS topic, but they get combined together in this single SQS queue that feeds the suppressor. So now between these two examples, you've seen us take a single set of standardized data, fan it out to two different applications, and then join it back together when we get to the suppressor. When you think about our requirement of rapid prototyping, this is fundamental to how that works. If you have an idea of a new technique, maybe you want to apply a new machine learning model to the data, you can create that application, subscribe back to the standardized data, put any potentially interesting events into the suppressor, and you've added a new component to the system and a new capability with minimal work. In the same way, you see any tip-offs that we would have suppressed, we go put in their own bucket, but any unsuppressed tip-offs are what we're actually going to investigate later. And so what I'll walk through on this slide is, here's how we process and investigate this data. It's likely going to look very similar to how your team's going to do it, maybe with different tools throughout the process, but a pretty typical investigation process. So we're going to take every one of those unsuppressed tip-offs. We're going to correlate it with other events that have happened on the endpoint. We want to know what other behavior, what other potentially interesting behavior is happening at the same time. Then we want to take all of that and we want to statistically model what is the expected impact of those events. Did we find them from pretty noisy detectors, or did we find them from something we absolutely know, is APT or a targeted adversary and is very, very high impact? That helps us put things in the right order for our team to investigate. Then we do the investigation. If we determine, if our security operations team says, hey, this is evil, we're going to classify it, and then we're going to mark the indicators of compromise to allow our remediation and response to move more quickly. If we don't determine that it's evil, and we say, I'm most certain that this is actually acceptable activity, this is where we may create that suppression rule that then feeds back into the suppression engine so that we don't have to do this exact investigation again. So now, once we've gone through the top part of that process and said, yes, based on this data, I do have a confirmed threat, let's talk about one fun thing we've learned over the last several years of how we can do this even better. Well, when you look at this based on certain types of data, there are some times when you absolutely know with complete certainty, when I see this behavior, it is evil, and it's this kind of evil. That's where what we call Autobots come into play. This is something sitting behind our system that, think of them as automated security operations part of the team. They get those events. They say, hey, based on this behavior, I know exactly what this is. The bot automatically classifies that threat. It marks the indicators of compromise. It ships the threat out the door and, to our customers' incident response teams. It's doing the same work our security operations team does. In fact, they exist because our security operations team wants to investigate and hunt for the most interesting behaviors. They don't want to be hunting for pups or for browser toolbars who, just continue growing, or even some of the new cryptocurrency miners. They want the bots to handle those, more monotonous or tedious investigations while they look for the more interesting attacks. So keep that in mind as you build your process. Always think about, what could I be automating end to end throughout this process? So finally, now that we know we've looked at all of this data, it's in a standardized format, we've detected what's interesting, we've suppressed out the uninteresting bits, we've investigated and confirmed this is a threat, now we remediate. Not really the focus of our presentation today, so something we can probably talk about in future presentations, but what you want to do is automate this as much as possible. The great thing is the data that your system is now built on top of is the best data to understand, how do I surgically do that remediation and response. So that brings us to the end of our process. Let's go back to our requirements and talk about, how does this system and this process meet your requirements for processing this data? When we look at scaling massively, big things that we've learned that are very helpful. AWS is key to that. Being one file in, one file out, focused components makes it simple to debug and process. Avoiding databases because they aren't as horizontally scalable as you'd like. Any sort of containers running on top of AWS is key. Tools on the maintenance side, like Terraform and Prometheus, CloudWatch and PagerDuty, are essential to be able to operate a system like this at scale without having to build a team of people who sit and babysit it all day long. And from a rapid prototyping side, let your team build in whatever tools are most familiar or most productive. For us, it's a lot of Ruby, a little bit of Python, some Go mixed in based on the actual capability we're developing, but all of them hang off of this pub-sub architecture that allows you to quickly prototype new components. On the side of lessons that we've learned over 4 years of doing this, I'm going to sound like I keep beating a dead horse on this, but it's essential that you build simple components. When you have simple components, they are easy to build, they're easy to debug. It's why we stick so closely to this principle of allowing components to take one file in and emit one file out. Related, you may ask, why are we storing every one of these intermediary results in a bucket? It seems wasteful from a storage perspective when you're just doing something as simple as taking data from a native format into standardized, for example. The good news is storage is relatively cheap these days, and it's well worth it for debugging purposes to have all that data at your fingertips. One of the principles we also adhere to is that we keep the same file name throughout these different buckets. This means from a tracing perspective, we can go all the way back to the beginning of native data coming into the platform and see as it processed through every step of the pipeline and what happened to it. It's a killer feature, I'd say, when you're building any system like this. Third, data absolutely has momentum. Your mass times velocity equation absolutely applies here. When you think about starting this and starting to look at this data, you're probably going to turn on one data source to start. You're maybe going to figure out, how do I get a record of every process start from my EDR platform or something like Sysmon into my pipeline? That's a great place to start. And then you're going to add a list of every network connection that happens to and from your endpoints. As you add each of those data sources, as you get more mass in your pipeline, everything is moving faster. Your components have more scale to keep up with. They have more impact if something goes wrong. And so it's something you want to prepare for. And even in some cases, you want to test and introduce, hey, what happens if I break one of these components? I should see my dead letter queue fill up, and then how do I reprocess all of those files? All of these challenges have relatively simple answers to them, and you'll do great when you test them and turn those capabilities on, but you want to test that before something actually goes sideways in the middle of the night. So now hopefully as we look at this and you think about this blueprint of processing all of this data, you feel a bit more like this Keanu Reeves. You can dive in a little bit more. All this material will be available after the fact to understand and start putting it in practice. But now we want to talk about what's this actually look like in practice with a case study. So we're going to talk about one of our favorite types of attacks here, Squigglydoo. And what does that look like as it infects an endpoint or happens on an endpoint throughout this processing system? So you can see here a command line that you can run on any system, runs red server 32, grabs a payload, thanks to the atomic red team sitting up there that'll actually execute on your systems, running scrubj.dll. This is Squigglydoo in practice. On the collection side, here's what this data looks like in this example collected from the Carbon Black Response project. What it's doing is we're seeing all of this data about what the system actually does. Here's the process command line showing what actually happened, as well as other metadata about the endpoint and the process. When we standardize that data, now you can see we've added a little bit more metadata at the top, telling us when we ingested it. What's the schema of this standardized data? We've also tidied up some of the field names to better fit downstream applications and what we've learned over the last few years. Then how do we detect it? Over on the left, you see what we call a detector looking for this specific type of behavior. In this case, it looks for any process who has a name of redserver32.exe, or it has an internal name of redserver32, and a command line that, when lowercase, includes scrubj.dll. It's just one of a dozen or so ways you can look for this type of attack. But in this case, over on the right, you can see the result of what happens when we actually flag this behavior. We can see that when this process executed, both the process name as well as the internal name matched our query here, as well as the command line included scrubj.dll. So we've identified this process does match our behavior. Next, we're going to check and see, have we investigated this specific behavior before and said it's okay? And so we execute a query against our suppression rules microservice, which has the big database of investigations we've done in the past. And we say, have I seen this specific set of techniques on this specific endpoint with this user, with this command line, all of that, and have I ever investigated it and said it's perfectly acceptable? And the answer on the bottom right there you can see is no, I've not suppressed that, I've not investigated that before. You can see for each of those different techniques, I have a null response, which means there are no suppression rules associated with this. So I do need to actually investigate this behavior. Here you'll see how we do that in the Red Canary Analysis platform. In this case, you can see Aaron here happened to be the lucky winner of this event when operating in our system. And this is what we call an event block. So this is a very condensed way to show what did an application actually do that triggered our detection systems. You can see our process with our command line, as well as at the top right, any list of all of the different detectors that identified this process and told us about what their expected impact or likeliness of being evil or bad is. When he does this investigation, in this case, definitely malicious behavior, so he's going to write up what we call a detection, classified at the top as malicious software, talks about the endpoint and the user associated with it. If you scroll down, you can actually see the different techniques that were observed. This is where our mapping back to attack comes in and shows you there's again our detector and what attack techniques were in play during this investigation. Finally, we see in the actual timeline showing what did we observe here, that we have a note again from Aaron talking about how this host is downloading a file remotely from GitHub, really taking that esoteric behavior and translating it into knowledge that any incident responder or any security response team can see and quickly understand, okay, this is what I'm dealing with. Again, all examples, your investigation platform is going to look differently. It may be in Splunk, it may be in other security tools, but the process is likely very similar. So finally, once we've done that, again, we're not talking about remediation in this process. Do want to say kudos. You can go look around and figure out how do I actually stop Squigglydoo. Our team says one of the best things to do, use your Windows firewall, prevent Reg Server 32 from making any outbound network connections. It doesn't need to do that, and so you can just stop it from doing that in the first place. So I want to end with our one marketing slide talking about what does Red Canary do and why are we here. Other than the fun we have in educating security teams like yours about how to build these systems and how to build better blue teams, what we do every day is we work with you to go out and deploy EDR sensors across your organization. We do this that we talked about today all day, every day, processing this data through our platform, doing detection and identifying new detection techniques, and then doing the investigation and preparing you to actually respond and remediate. And we give you that automated and orchestrated response through our platform so that you can cut your mean time to detection as quickly as possible. That's us in a nutshell. You can see us at a lot of different conferences and learn more on our blog about how we actually do this. But that really brings us to the end today of what we wanted to talk about. And so now I want to open it up for any Q&A that you may have.
All right, thanks, Brian, for that great presentation. We do have some questions ready for the Q&A. However, if anyone has a question for our presenter, please enter it into the questions window now. Our first question is, how does on this endpoint apply in an ephemeral environment like EC2?
That's a great question. So when you look at any data happening on any of your endpoints, you really want to treat them all as if they may be ephemeral. And so when you collect data from an endpoint sitting in EC2 or inside an auto-scaling group, you're going to assume that they may come online, they may live for minutes, or they may live for hours, and then they could disappear. And so a key part of doing that is you need to understand and you need to tag data coming from an endpoint with metadata about the endpoint so that you know what it was at that time, right? A lot of teams struggle with asset management and inventory of those auto-scaled systems. And so you can't always depend on there being some database that's going to hold all of that information, let's say like Active Directory. And so when you collect telemetry off of an endpoint, you have to you want to put that data identifying the system inside the actual data coming from the system so that it's always processing through your platform and you can tie back to that. Hopefully that makes sense. There's a lot of techniques you can use on how you collect the data in order to make that possible. But when you start treating every endpoint as if it might be ephemeral, it starts getting you thinking in the mindset of how you're prepared for more and more systems moving to the cloud.
All right, thank you. Could you build this type of platform in another cloud provider?
Yeah, absolutely. We know, we've looked several times at the different data types and others provided by Azure, for example. They have the same fundamental data types and concepts as S3 buckets, SNS topics, and SQS It would translate there very well. In fact, it's one of the biggest arguments why your team should be using Terraform if you are doing anything in the cloud, because when you have all of your architecture defined inside of a tool like Terraform, it's very easy to just translate from one cloud provider to another.
All right, thanks, Brian. How much do you detect with threat intel versus behavioral?
For us last year, we saw threat intelligence contributed, I think it was 7% of all detections we identified. The other behavioral indicators, whether we're looking for patterns mapped back to MITRE's attack framework or other adversary techniques, made up 93%, the other 93% of what we detected.
Thank you. Would this work in Oracle Cloud?
That is a great question. I actually am not familiar enough with the Oracle Cloud to know for certain. What I will say is, you even can think about some of these systems and think about how you might apply them outside of any cloud system. You know, we're using the cloud here as our data storage mechanism with S3 buckets, as well as our queuing services and a place to run applications. There's nothing that says you couldn't run it in, you know, I'd assume Oracle's cloud or even your own data center using the same Kubernetes subsystem, you know, and maybe an NFS mount instead of the S3 buckets as the way to process data between them. So definitely possible, probably not as easy, or I'd say definitely not as easy as turning it on in any cloud provider.
All right, thank you. If I could start anywhere, where should I start?
Good question. I'd definitely start with standardizing the data, because long-term, that's going to be some of the biggest bang for your buck. Once you have that data all in a standardized format, it gives you a very simple way to build applications later. But standardizing data in and of itself doesn't move your security program forward. I think if I were to pick one maybe data type, and let's even say one field to focus on first, I'd start looking at command line. If you can get data of every single process and command line that executes across your environment, you can start building really good detection techniques on top of those systems and identify the interesting behavior that you want your team to investigate.
Thanks, Brian. That's all the questions I see for today. Do you have any closing thoughts you'd like to share?
Just want to thank everyone for coming here. Hopefully it was a very informative blueprint on how you can prepare your team to do better security through processing more data. And don't hesitate to reach out to us or come over to the Red Canary blog to learn more.
All right, well, thank you so much, Brian, for your great presentation, and to Red Canary for sponsoring this webcast, which helps bring this content to the SANS community. To our audience, we greatly appreciate you listening in.